Know me, I am a Black Hole Initiative Fellow here at this separate institute at Harvard University. I work on the theory surrounding the formation and evolution of supermassive black holes over cosmic time, both thinking on scales of the observable universe and very high redshift, as well as the central engine, where I spend a lot of time working on the Event Horizon Telescope. And I believe that this is all very necessary for a full and comprehensive picture of supermassive black hole astrophysics. Virtually all models of galaxy formation require active galactic nucleus or AGN feedback in order to curtail star formation in the most massive halos. Without such energy injection, clusters will overcool, form too many stars. You end up with gigantic spiral galaxies that we do not see in the universe. And yet the exact ways in which black holes accrete their matter and feedback onto the inner environment and form have not been fully understood. If you look at this very well-studied example, M87, you can see the problem. We have structures, these jets that are emanating from the center of these galaxies, spreading out sometimes kiloparsecs to megaparsecs in size, that are being launched by structures that are down at the micro to milliparsec scale, depending on the mass of your black hole. Such a system can never be fully captured in a single simulation, and so we need to be very clever and tackle the problem in many different ways to fully understand what's going on. And so a multi-pronged approach is needed to piece together all of the different parts of astrophysics. And there are a few different ways that AXIS is going to be tackling several open questions that I would like to go over today. One is seeding, how the very first black holes in the universe that would grow to make these monstrous, sometimes 10 to the 9 or 10 solar mass black holes proceeded. Next is dynamics, where we're very interested in dual and offset, or what I like to call wandering black holes. And then there are some synergies that I'd like to point out where we can constrain the central engine via these X-ray cavities that we'll be able to constrain, along with things that we'll be able to do in concert with other instruments like the Event Horizon Telescope. So first, let's talk about seeding. When it comes to forming the first progenitors of the most massive black holes, theorists have been able to run their imaginations wild for decades. Already in 1978, we see this plethora of pathways diagrammed by Martin Rees here. And in fact, this web has only expanded since then. But now models are growing more and more physical, now that we have hydrodynamical simulations that can achieve greater resolution, but they're very much in need of more observational constraints. There's a nice comprehensive review called Titans of the Early Universe by Woods et al. 2019 that I recommend if people would like to know more about this. Now, while there are many different and probably mixed channels of black hole seeding that can be operating in the universe, it is often useful to compare and contrast the two extremes, because if you can distinguish these two cases, then you can, that's an upper limit on what you can do in determining the differences between other classes. So one is light seeds, which would be abundant and low mass, maybe around 100 solar masses, such as the remnants of the very first population of stars. This is a kind of obvious channel because we know this is how black holes form in the local universe. However, these things tend to form in places where stellar feedback has already blown away the gas that you would like to grow your black hole. And these have particular problems trying to explain, especially the very high mass black holes, 10 to the 9 or 10, that are already observed at redshifts of 6 and 7. And so this, among other things, has motivated heavy seeds as an alternative, which are supposed to be rare and high mass, sometimes up to 10 to the 6. And these are supposed to form from the direct collapse of primordial gas clouds. Essentially, you need to have a whole bunch of mass in one place where the gene's mass is kept very large. Usually, that amount of mass in a cloud would like to fragment into a cluster of stars, but what is usually invoked is a background of Lyman-Werner photons that will dissociate the formation of molecular hydrogen and make sure that only atomic hydrogen is the coolant, keeping the gene's mass very high. So important constraints distinguishing these kinds of models include high redshift luminosity functions, low redshift occupation fractions, gravitational waves, and high redshift quasar masses. There are lots of degeneracies involved in each of these, and so it's important that we have multiple different ways to tackle this problem. One way to get an understanding of how these things leave imprints on our observables is by trying to place these in a full cosmological framework. And what I've used in the past is called a semi-analytic model, or a SAM. The idea is to try and self-consistently and really rapidly produce a suite of different observables. So this is in contrast with a full-blown cosmological simulation, where one treats all of the black holes, stars, gas, and dark matter as separate particles, and tries to evolve these structures in more detail. Here, things have been stripped down to the bare bones to try and produce a very simple, but easily understandable and easily produced picture of the universe. Here we start off with some galaxy assembly histories where we've put together lambda CDM cosmology and made some assumptions about the galaxy halo connection, make some assumptions about seeding and accretion and dynamics of black holes. And what's nice about this method is that you can self-consistently and simultaneously make predictions for a whole slew of observations: black hole host galaxy relationships, luminosity functions, backgrounds in, say, the X-ray and infrared, clustering signatures, and gravitational waves. In doing this technique, I achieve a very large effective volume and effective resolution. So we go down to 5 times 10 to the 6 solar mass halos, all the way out to redshift of 20. And this is important because this is where we believe that seeding actually proceeds. While cosmological simulations will treat the assembly of black holes at low redshift much more carefully, they do not have the resolution to go that far and in redshift and that low in mass. And what's nice is that using this, one universe will only take a few hours just using a single core. Conceptually, I like to think of the local relationships between black holes and their hosts as setting a boundary condition, like the M sigma relation, whereas luminosity functions, that which we can probe now with access at higher redshift than we have today, will constrain the overall growth rate, with some degeneracies about linking particular accretion rates to a particular black hole. In more detail, suppose we want the growth history of a black hole that ends up in some host halo of some mass at redshift of 0. In this model, we first generate a merger tree using a press-sector approach, going all the way out to redshift of 20. And in the very early universe, what we prescribe to be redshifts of 15 to 20, we seed these halos using either heavy or light seeding scenarios. We don't actually track the evolution of the galaxy or its gas fraction, use instead empirical relationships that are extrapolated out to these redshifts as a probe of this for more efficiency and more focus on black holes. Then at every time step, we say that in this particular picture, AGN are driven by mergers, and they grow until they reach the M sigma relation. Halos will merge after a dynamical friction timescale, and then their black holes may also merge, and you just keep doing this until you get to redshift of 0, or whatever your target redshift is, repeating for different halo masses, different assembly histories, and weighting according to their halo abundances to get your ultimate luminosity functions. So what we've used in the white papers are some predictions that we made out past redshift of 6. These are some predictions from the models going from redshifts of 6 to 12. While we were preparing this, those points in the background at redshift of 6 come from Hopkins et al. 2007. There are now more recent formulations of this. Here we have light seeds as light colors, as warm colors, the red and orange, and the heavy seeds as the cool colors. You'll notice that at redshift of 6, they basically agree, same at redshift of 7. But if you keep pushing out in redshift, something special starts to happen. Exactly when this happens will be highly sensitive to one's accretion prescriptions as well. But focusing here at redshift of 10, you can see that these curves have diverged. And physically, it's pretty simple what's going on. The heavy seeds started off with a larger initial mass. And that means that in this framework, where things are Eddington limited, they're able to achieve a higher mass and therefore shine at a higher luminosity earlier on in the universe. So we've worked to try and do this more carefully. This is our white paper version, which is done with Stefano and Nico. You can see as well some comparisons with cosmological simulations, for example, as this large band over here. There's actually a very large range from the Cosmosims that they don't actually reproduce luminosity functions all that well, and they disagree with each other, and they're very expensive to rerun. And so doing this over and over again is to get actual matches to luminosity functions that we observe would not be tractable. But we see here that, again, luminous sources will appear earlier for the heavy seeds. And there is a lot of uncertainty in terms of exactly how much, how many sources we will see. But I think that anything that we see, particularly out at redshift of 10, would be interesting. All of these uncertainties are simply something that it's difficult to marginalize given our current knowledge in the theory, and any measurement of these luminosity functions will be constraining. I'd like to make the point that this is a special epoch in cosmic history. It's only at these very large redshifts, past 6 and 7, that when we see these black holes that are already 10 to the 9 solar masses, one has to start invoking either heavy seeds and or continuous super Eddington accretion in order to explain their very high masses. And so this allows us to peer into a special epoch where we're starting to put more stringent constraints on this combination of seeding and growth and accretion modes. Now, I've mentioned that there are degeneracies, but that there are also observational probes that we can use to break them. The same semi-analytic model we use to make predictions for LISA. And so you can see the distributions of events, both in terms of mass on the left and in terms of redshift on the right. And the numbers are basically what you would expect intuitively. The heavy seed mass function will drop off at some point, basically just sensitive to the initial mass function that's assumed, whereas the light seeds will continue to produce these black hole mergers at, in this case, 10 to the 3. The heavy seeds will also produce more mergers out at redshift of 15, if we're so lucky to discover one, which will enable us to have an additional probe of these initial masses. But there's now a new degeneracy relating to the dynamics of these black holes. Fortunately, Access will also allow us to constrain this part of black hole astrophysics as well by probing dual, offset, and wandering black holes. I've done some work in this field as well, and what I've done involves what are called these Romulus cosmological simulations. What's nice about these simulations, which consist of both a galaxy cluster and a 25 megaparsec cube volume, is that they have realistic seeding that's actually meant to emulate direct collapse black holes, and realistic dynamics where corrections have been made to account for missing dynamical friction that you would usually have when you have gravitational softening and limited resolution, a kind of treatment that has been becoming more standard nowadays. And there's also a large dynamic range in halo mass that you can get by combining these two sets of simulations. Part of the main results coming out of these is that we found significant delays from galaxy merger to black hole merger and a significant stochastic component. It's not easy to predict how much of a delay you get based on the analytic, say, Chandrasekhar dynamical friction formula, because cosmological environments are simply messier than one would expect. And there are different dependencies on, for example, the central concentration of stars in a galaxy. And so there can be delays that can range up to gigayears sometimes between galaxy merger and black hole merger, whereas you might expect a prompt merger instead. Whether or not and when these black holes merge will affect things like the gravitational wave event rates and the mass assembly of the most massive black holes. This is a visualization of how these might be distributed in a Milky Way-like galaxy by Michael Tremmel in his 2018 paper. In a couple of papers in 2021, we looked into wandering black hole demographics, which are essentially just a synonym for dual and offset AGN, as long as they're accreting. So here, if we look at the top first, we have histograms of the number of central black holes as a function of halo mass on the x-axis, and then redshift as these different panels. What's nice is that there are X-ray constraints on this as well, which potentially AXIS may also make new strides on. But the point is that these simulations correctly reproduce the central AGN occupation fraction, giving us confidence in what it predicts for the wandering population. And what we see is very interesting, which is that the number of wanderers grows linearly with the halo mass. While Milky Way-like halos may have about 10 wandering black holes, the main halo of Romulus C, which is a 10 to the 14 solar mass cluster, has about 2,000. That is, these wandering black holes vastly outnumber the centrals. And this is, in fact, even a lower limit because we don't take into account ejections from a gravitational wave recoil or potential multi-body interactions that may occur at the centers of these galaxies if multiple black holes make it there at the same time. So this is what this looks like from the theory perspective, not necessarily what you would see in X-rays, but I'll get to that. And the one that we have on the right here is the central group galaxy of one of these groups in Romulus, where you can see hundreds of black holes wandering through the halo. What's interesting about this is that they're essentially missing from the black hole census. What we like to do when making comparisons of the evolving black hole population in theory with the observations is make a link between the luminosity functions we observe and the total amount of accreted mass. But when we do this, we only know about the mass that is at the centers of galaxies, because those are the ones that we can actually count. Fortunately, locally, it turns out that wanderers only amount to about 10% of the black hole mass budget, no matter which way I cut it. These different colors are different criteria for a wandering black hole. And so that's okay for a redshift of 0. But if you go to high enough redshift, it turns out that actually most of the black hole mass is in wanderers. This is likely due to the increased merger rate and the finite amount of time required for black hole mergers to occur following a galaxy merger. In the follow-up paper, we looked into the observational signatures and found that these wandering black holes may indeed shine, as you might expect. These are now what we would call these dual or offset AGN. This is a particularly spectacular example that we found. This was meant to emulate Chandra on the right here. So the PSF you might want to blur out by a factor of 2 in your head when comparing to what AXIS might be able to do. But I think Baymax would be able to do a fine job at distinguishing multiple sources here. We've also quantified the probability of a dual AGN. So in this particular plot, we assume that there exists a primary AGN that has an X-ray luminosity above 10 to the 41 ergs per second. And then ask, what is the probability that there's a second one in the same halo that has a brightness ratio of 50% in orange or 10% in purple? And there are some interesting trends as a function of redshift and stellar mass. At higher redshift, you see that there is a larger dual AGN probability. In fact, it's most of these galaxies at a redshift of 4. And this is probably due to the fact that there are more frequent mergers and more plentiful gas, and at higher masses as well, at a fixed redshift, especially at low redshift. There are going to be more wandering black holes, as we discussed earlier. And one thing we realized is that these wandering black holes may, in fact, outnumber the central ones outright. And if you make histograms of just black holes as a function of their mass, what fraction of them are actually at the centers of galaxies? It turns out that this drops below 50% once you go below 10 to the 7 solar masses. This means that potentially your typical 10 to the 6 solar mass black hole is not something like Sagittarius star, but something that's wandering in the outskirts of some galactic halo. This may have some implications that we speculated about on tidal disruption event rates. If such wandering black holes are able to retain a stellar component from which they could tidally disrupt stars, then perhaps the majority of TDEs may come from these wanderers. Finally, I'd like to touch on some central engine science, since I spend so much time working on the Event Horizon Telescope. With EHT studies right now, oh, sorry, I see a question from Nico. Do you expect similar numbers of wanderers in early and late type galaxies? Yes, we do, but I expect a difference in their observability. So in order for them to actually be accreting, they need to run into some amount of gas. Actually, a more robust treatment of this comes from one of Fabio's students, whose last name I'm currently forgetting. So that would be Pacucci and Narayan as second and third authors. But there should be a similar raw number, which may be most relevant for TDEs. But if you wanted to just find them as dual and offset AGN, I would expect that there would be a difference between the early and late types. Okay, back to where I was. So with the Event Horizon Telescope, we now have these images of black holes at the centers of our galaxy, Sagittarius A star, and at M87. Right now, we have static blurry donuts, but in the near future, and certainly by the time that Axis would be flying, we're expecting to have these spectacular movies like you can see here on the right. This is a simulated GRMHD simulation on the left, and actual simulated array performance and image reconstruction on the right. You can hardly tell the difference. We expect to be able to make movies that will capture simultaneously the accreting material in the disk, as well as the feedback coming from the jet that will emanate out onto kiloparsec scales. Oh, this one is M87, by the way. No, we're not sure if our own black hole will have a jet to observe in the same way. Now, X-ray constraints have already been pivotal in our interpretation of Sagittarius star. If you check out our theory paper surrounding the release of this image, we found that this was very important for distinguishing different classes of models related to their magnetic field state. So there are these strongly magnetized models called magnetically arrested disks, or MADS, as opposed to more weakly magnetized models, standard and normal evolution, or SANE, very much intended. Although unfortunately, it looks like MAD is becoming the standard, which is going to be confusing moving forward. X-ray constraints were very important for breaking degeneracies, and they prefer these really highly magnetized models, as well as two temperature plasmas, by which I mean models where the electrons have actually achieved lower temperatures than the ions, which is something that we expected just because these flows are so rarefied. They're not able to reach thermal equilibrium. Now, there's already been a great talk in this series about X-ray flares, but I wanted to touch on latest developments on the GRMHD side. And this connects with this particular class of models that we seem to be moving towards. So there are these what we call flux eruption events, or which are essentially magnetic reconnection events in these MAD models that produce a natural mechanism for flares, which will be another way to test our models for these central engines. And what we think is happening is shown here in, so we have this movie on the bottom where we have a MAD, where I've ray traced the emission of thermal electrons in log scale. Occasionally, as more magnetic flux is getting advected onto the black hole, the black hole will reject it. It has reached a maximum amount of magnetic flux. Magnetic reconnection will occur, heating up the surroundings and causing what looks like a hole in this simulation with just thermal electron distributions. But what we think could show up as a multi-wavelength and polarized flare that enables synergies between AXIS and a plethora of other environment instruments that will allow us to probe black hole physics and plasma physics. And so this is an important way that we can continue to test our understanding of these black holes. These MAD models also produce powerful jets, and these are actually powered by spin extraction, what's called the Blandford-Znayak mechanism, which enable us to actually link feedback signatures, these X-ray cavities that we'll be able to observe as a function of redshift, to spin evolution. So it turns out that these jets spin the black hole down at a cosmologically significant rate. This is something that we have worked on recently in Narayan et al. 2022, and my most recent paper that came out a few months ago, or actually it just got published last week, actually. And this may impose evolutionary constraints on maintenance mode AGN that would inflate cavities. So the point is that these jets are very efficient. Actually, they can be over 100% efficient in terms of jet power you get out for compared to the rest mass energy going in, because that's actually coming out of spin energy. Now this places some constraints on how much accretion could be occurring over cosmic time if this process is going to spin your black hole down. This is something we thought about a little bit based on the constraints that we have already that go out to redshift of around 1 for these X-ray cavities. But if we continue to push our redshift boundary, this may become more and more interesting. We think, for example, if you look at this plot on the bottom right, if you start out with a black hole that is a spin of 0.9 and make it produce maintenance mode AGN in the form of these jets for a gig year, at, in this case, an Eddington ratio of 3 × 10⁻⁻3, it would actually spin down to about 0.5. And the higher we go in redshift, the more interesting this becomes, because this may require some kind of rejuvenation of the spin in order to continue performing radio mode feedback. In addition, we expect actually to get spin measurements of these kinds of maintenance mode AGN with the next generation Event Horizon Telescope, where we will use the millimeter polarization pattern. There's a twisty pattern related to the magnetic fields, which are frame dragged by the spin of the black hole, that we can use to measure spins. And so there's going to be lots of ways that AXIS will tackle black hole evolution and synergies with many different instruments. I'll just leave my conclusions here and take questions. Thank you.
Great. So yeah, we have time for a couple of questions. You can either post them in the chat. So that was really interesting about wandering black holes. Can you tell me a little bit more where that 700 parsec number comes from? Is that just some typical scale where...
Oh, that's just resolution.
Oh, okay, it's a resolution.
Yeah.
I didn't know it was a scale where like things will, go down to, 10 parsec or something.
No. There's nothing special about that scale.
Great. Are there other questions? Rick, you want to ask a question?
Yeah. Can the non-pulsing ultraluminous X-ray sources that have been seen nearby be examples of these wandering guys?
They certainly could be. So in particular, I don't know very much about ULXs or what the non-pulsing category means. But there's this interesting candidate wandering black hole that I kind of skipped over, which is in this lenticular galaxy separated by 25 kpc from the center. So if there's evidence for a black hole that would have intermediate or supermassive mass offset from the center of a galaxy, then it's quite plausible that this would be a wanderer. And really, these are natural consequences of hierarchical structure formation. They really should be there. It's just a matter of quantifying how many there are and how long it takes for them to get to the center of the galaxy.
Okay, thank you. The pulsing part is some of these have been seen to be pulsing, so we think it's super accretion onto neutron stars. That's all.
Gotcha. Okay.